From myth to machine, the ancient quest fulfilled. For centuries, the dream of turning common metals into precious gold captivated the minds of alchemists. They toiled in dimly lit laboratories, surrounded by strange concoctions and arcane symbols, all in pursuit of the legendary philosopher's stone. This mythical substance was believed to hold the key not only to transmuting lead into gold, but also to achieving immortality. While their methods were rooted in mysticism rather than empirical science, their ambition was truly profound. They sought to understand and manipulate the very essence of matter, a quest that, in a way, foreshadowed the endeavors of modern physics. The allure of this transformation was powerful, representing ultimate mastery over the natural world. The idea of transmutation, changing one element into another, was once thought to be pure fantasy, a relic of a pre-scientific age. However, the alchemists, for all their unscientific approaches, were asking fundamental questions about the nature of materials. What makes lead lead and what makes gold gold? They didn't have the tools or the understanding of atomic structure that we possess today, but their relentless curiosity laid a peculiar kind of groundwork. They were driven by a desire to unlock the secrets held within the substances around them, a desire that resonates deeply with the scientific spirit of inquiry that propels research forward in our modern era. This age-old quest has, rather astonishingly, found a form of realization in the heart of modern science. Now, in an almost unbelievable turn of events announced just days ago on May 23, 2025, scientists at CERN, the European Organization for Nuclear Research, have achieved this very feat. They have successfully transformed lead into gold. This isn't magic, and it certainly won't make anyone rich in the traditional sense. Instead, it's a stunning demonstration of our understanding of nuclear physics and our technological prowess. The ancient dream has been touched not by mystical incantations, but by the precise and powerful application of scientific principles. It's a milestone that connects a distant, almost mythical past with the cutting edge of contemporary research and discovery. This remarkable achievement underscores a fascinating journey of human understanding, from the speculative art of alchemy to the rigorous science of particle physics. While the alchemists sought wealth and perhaps eternal life, today's scientists seek knowledge and a deeper comprehension of the universe's fundamental laws. The gold produced is infinitesimally small, its value purely scientific. It represents a triumph of human ingenuity, a testament to how far our exploration of matter has come. The methods are vastly different, yet the core fascination with the transformation of elements provides a compelling link across the centuries, showing how persistent human curiosity can lead to extraordinary outcomes. CERN's Colossus, the Large Hadron Collider at work. The heart of this incredible scientific breakthrough is the Large Hadron Collider, or LHC, located at CERN, straddling the Franco-Swiss border. This is no ordinary machine. It's one of the largest and most complex scientific instruments ever built by humankind. Imagine a colossal circular tunnel, 27 kilometers in circumference, buried about 100 meters beneath the Earth's surface. Within this tunnel, powerful superconducting magnets, chilled to temperatures colder than outer space using sophisticated cryogenic technology, guide beams of particles. These particles, often protons or heavy ions like lead, are accelerated to almost the speed of light, racing around the ring in opposite directions. The primary purpose of the LHC isn't to mimic alchemy, but to explore the fundamental constituents of matter and the forces that govern their interactions. Scientists use it to recreate the conditions that existed just moments after the Big Bang, hoping to unlock some of the deepest mysteries of the universe. When these particle beams, traveling at incredible energies, are made to collide, they shatter into a shower of new particles. Gigantic, highly sensitive detectors are positioned around the collision points to meticulously record the properties and trajectories of these fleeting products. It is through analyzing these collisions that physicists test theories, discover new particles like the Higgs boson, and probe the very fabric of reality. For the experiment that successfully transmuted lead into gold, the LHC was configured to accelerate beams of lead nuclei. These are atoms of lead that have had their electrons stripped away, leaving just the dense, positively charged core. The sheer power of the LHC is required to get these heavy nuclei moving at such phenomenal speeds, over 99.99% the speed of light. The engineering and precision involved are truly mind-boggling. Thousands of magnets must work in perfect concert, controlled by complex computer systems, to maintain these beams and steer them towards their designated interaction points within the detectors. It's a symphony of advanced physics and engineering on an immense scale. The environment inside the LHC is one of extremes: extreme speeds, extreme energies, and extreme cold for the magnets. It's this ability to create and control such extraordinary conditions that allows scientists to perform experiments that would be impossible anywhere else on Earth. The LHC is essentially a discovery machine, pushing the boundaries of what we know and what is technologically feasible. While the transformation of lead to gold is a fascinating byproduct of its operations, the LHC's broader mission is to expand our understanding of the fundamental building blocks of the cosmos and the intricate rules that govern their behavior, from the smallest scales to the largest structures in the universe. The fiery dance transmuting lead in the ALICE experiment. The specific experiment where this modern-day alchemy occurred is known as ALICE, which stands for a Large Hadron Collider experiment. ALICE is one of the major detectors at the LHC, specifically designed to study the physics of strongly interacting matter at extreme energy densities and temperatures. Its focus is often on recreating and analyzing a state of matter called quark-gluon plasma, which is thought to have existed in the first few microseconds after the Big Bang. To do this, ALICE observes collisions of heavy nuclei, such as lead, which provides the perfect conditions for observing the transmutation we're discussing. It's within these incredibly energetic encounters that the transformation takes place. During the ALICE experiment, two beams of lead nuclei are accelerated in opposite directions around the LHC ring. While many experiments focus on direct head-on collisions, the transmutation into gold occurs through a slightly different process. As these incredibly fast-moving lead nuclei pass very close to each other, sometimes without physically smashing into one another, they generate immensely powerful transient electromagnetic fields. These fields are among the strongest that can be produced and studied on Earth. It is these ultra-strong fields that interact with the passing lead nuclei in a process known as electromagnetic dissociation, which is the key to this transformation. A nucleus of lead, chemical symbol Pb, normally contains 82 protons. Gold, chemical symbol O, on the other hand, has 79 protons. The intense electromagnetic fields generated during these near misses or ultra-peripheral collisions can be so powerful that they excite the lead nuclei. This excitation can lead to the ejection of a few constituent particles, including protons. In this specific instance, the electromagnetic interaction effectively shakes or strips 3 protons from some of the lead nuclei. When a lead nucleus loses exactly 3 protons, its atomic number changes from 82 to 79. And just like that, what was once lead is now fleetingly gold. Confirming such a subtle transformation amidst the chaos of high-energy particle interactions requires incredibly precise detection. This is where another piece of sophisticated equipment comes into play: the Zero Degree Calorimeter, or ZDC. The ZDCs are positioned far down the beamline from the main interaction point of ALICE. They're designed to detect particles that are only slightly deflected from the beam path, such as the newly formed gold nuclei. By identifying these nuclei and measuring their properties, scientists can confirm that the transmutation from lead to gold has indeed occurred. This confirmation is vital, turning a theoretical possibility into an observed scientific fact, providing crucial data. Beyond riches, the true gold of scientific discovery. While the headline "Lead into Gold" evokes images of alchemical riches, the reality of this achievement at CERN is far removed from any notions of material wealth. The amount of gold produced is astonishingly tiny. During the lead-lead collision cycles, the LHC produces approximately 89,000 gold nuclei per second. This might sound like a lot, but nuclei are incredibly small. Over an entire operational campaign, like the one from 2015 to 2018, an estimated 86 billion gold nuclei were created. Yet this vast number translates to a mere 29 picograms of gold. That's 0.0000000029 grams. This quantity is so minuscule it's invisible to the naked eye and far too small to ever be collected or used. Furthermore, the gold nuclei created in the LHC are not stable, long-lasting treasures. They are typically produced with high energy and exist only for fleeting moments before they either hit the walls of the detector apparatus or decay into other particles. So there's no stockpile of collider-created gold being amassed anywhere. The cost and energy required to produce even these infinitesimal amounts far exceed any monetary value the gold itself could ever have. Therefore, the objective of this research is unequivocally not to produce gold for commercial purposes or to enrich CERN's member countries. The focus is entirely on fundamental science. The true value of this modern transmutation lies in the invaluable scientific data it provides. Specifically, these observations are crucial for refining and validating models of electromagnetic dissociation. Understanding this process is incredibly important for the operation of the LHC itself and for the design of future, even more powerful particle accelerators. Beam losses, where particles are lost from the main beam, can be a significant issue in accelerators, potentially causing damage or limiting performance. The electromagnetic dissociation of lead into gold is one such process that contributes to these beam losses. Studying it helps scientists better predict and mitigate these effects, leading to more efficient and robust machines. This achievement at CERN, then, is a profound victory for science. It represents the fulfillment of an ancient dream, not through magic, but through the rigorous application of nuclear physics and advanced technology. It showcases our deepening understanding of the atom's core and the fundamental forces at play. The insights gained from observing lead turn into gold, even at such an incredibly small scale, contribute directly to our ability to explore the universe's most fundamental questions. It's a beautiful example of how pursuing pure knowledge can lead to fascinating, almost poetic connections with the past, while simultaneously paving the way for future discoveries. This is science at its most inspiring, turning the stuff of legend into tangible, measurable reality for the sake of understanding.